far, we've been completing the square to convert from standard form to vertex form so that we could graph. And the primary reason we needed to do that was to be able to find the vertex. We can find the intercepts, which we get the y value of the y-intercept by just plugging in 0 for x. We get the x values of the x-intercepts by setting this equal to 0 and solving, and we've got other techniques for that. But if I want to find the vertex, it seems like I have to complete the square. What I'm going to do here is I'm going to take a generic one of these, and I'm going to complete the square there. And I'm going to just look at the results. I should then be able to describe things in terms of these numbers, a, b, and c. I'm going to see if I can describe my vertex that way so that there's maybe a shortcut so that I don't have to complete the square each and every time. I'll just remind you that a has one restriction on it. If it's a quadratic, we have some x squared, so a isn't 0. That's all I know about a. I know nothing about b and c. So we've got f of x is ax squared plus bx plus c. Remember, I'm hoping to make those first two terms that have x's in them be a multiple of a perfect square. So the first thing I want to do is factor out that a from just those first two terms, and that plus c can sort of hang out while we're doing our work in here. Now if I pull out the a here, I'm left with one copy of x squared. Here, I want to remember that factoring out is like dividing out by a. So I'm going to have b divided by a copies of x. If I double check that, if I distributed that a back through, here this a would cancel with the a in the denominator, and I'd be back to having b copies of x. Notice it is necessary that we know that a isn't 0 in order to be able to factor it out like that. Okay. Now, we're hoping to make this quantity in parentheses look like x plus d squared, which is 2 factors of x plus d FOILed out. And again, that's x squared plus 2 copies of dx plus d squared. Now, by factoring out the a, we've made it so that we have just one copy of x squared, so our first terms match. If we move to the x's, the number that I want to have is 2d. The number that I do have is b over a. To solve for d, I would divide by 2. Remember, that's the same as multiplying by 1/2. So my d is going to be b over 2a. All right. With that choice, these first two terms match the first two terms of my formula. Now d squared would just be b squared over 4a squared. Square the b, square the 2, square the 4, square the a. Okay, so now I would say this is a times x squared plus b over ax. I would add and subtract my d squared. So plus b squared over 4a squared minus b squared over 4a squared plus c. Now these first three terms match my formula for a perfect square. So I'm going to distribute the a to those first three terms, x squared plus b over ax plus b squared over 4a squared. And I'm going to distribute the a to that fourth term, which is going to give me minus b squared over just 4a. That a will cancel with one of those factors of a. And then there's my plus c. Okay, and now, if I just gave you this and said factor it, it looks kind of intimidating. But because we completed the square, we know it factors as x plus d, and our d was b over 2a quantity squared. And then we're going to have plus negative b squared over 4a plus c. Okay. Now, if I look at that, I can figure out what the vertex is, because these numbers are going to give that to me. What I'm most concerned with, because I hate memorizing formulas and I don't want to have to memorize a whole lot, what I'm most concerned with is that. the x value of the vertex is just the opposite of b over 2a. Remember, it's going to be the number that we're subtracting from x. So if it's written as an addition sign, I need to view that as subtracting the opposite of b over 2a. That's the x value of the vertex. And that's relatively short, relatively simple to remember. And I'm going to, in a little bit, be able to give you another technique for remembering it. I'm not going to bother to memorize that, because if I can get the x value of the vertex, I can find the y value by just plugging that in. So the y value of the vertex, once I have the x, that's just my function evaluated at the opposite of b over 2a. Nice. So, having completed the square in this generic example, I can now use those results as a shortcut to go right to the x value of the vertex, which I can then plug in to get the y value of the vertex without having to complete the square. Let's just take a look at an example. Let's suppose I had f of x equals negative 2x squared plus 4x plus 6. Okay. And let's try to graph that, including the vertex and the intercepts. Okay. I will point out that's my a right there. Because it's negative, I know we open down, because the a here is going to be the same a I would have in vertex form. So that means I'm taking my parent function and I'm multiplying by negative 2. That does that vertical flip. So the sign of a is going to tell me whether my parabola opens up or down. All right, so I'm going to just write down a is negative 2, b is 4, c is 6. I often find it helpful to just write that down so that I'm not trying to remember, wait, a stands for what, b stands for what, at the same time I'm doing calculations. So now I can say the x value of the vertex is the opposite of b over 2a. If b was 4, the opposite of that will be negative 4 over 2 times negative 2. So that's just negative 4 over negative 4. That's just 1. So the x value of the vertex is 1. The y value of the vertex is going to be the y value I get when I plug in 1. So that's f of 1. Okay. 1 squared is 1. So I'm going to get negative 2 plus 4 times 1. So that's negative 2 plus 4. That's 2 plus 6. That's going to give me 8. So my vertex is at 1, 8. Fabulous. Now, I can find the intercepts. The y-intercept, that's going to have an x value of 0, and the y value is just what I get when I plug in 0. Lovely thing about plugging in 0 in standard form is every term with an x in it gets killed off. I'm just going to get 0, 6. So there's that. Notice that confirms what I already knew, which is that this should be opening down because this point is below here. So that vertex is a high point, which is great. And now I need to get the x-intercepts. Okay. Now, to get the x-intercepts, I just need to know that the y value will be 0, and I set my function equal to 0 and solve in order to get the x values. I have two options. One, I can try to factor. There will be some times when your equation doesn't factor, but there are still x-intercepts, and then you have to use the quadratic formula. If it factors, you can either factor or use the quadratic formula. If you know there are no x-intercepts, if this had been the vertex and we'd opened up, I wouldn't even bother looking for x-intercepts. But here I know there are some. I'm going to try factoring, but I will just remind you after we do it that way what the quadratic formula is as well. So if I wanted to factor, I'd first of all try factoring out that negative 2, because all of these numbers are even, and I can get to smaller numbers if I factor that out. Also, when I'm factoring, I like my squared term to be positive. Okay, so this will be minus 2x minus 3 equals 0. Now, I can divide both sides by that negative 2. So I just have x squared minus 2x minus 3 equals 0. Now I'm hoping that that's the result of foiling. So when I'm factoring a trinomial like this, I'm basically unfoiling. In order to have x squared, I can see I'd have to have an x and an x. Now when I'm unfoiling, I usually actually unfloy. So I'm going to now look at the last terms. I need numbers that would multiply to give me 3. If I just try factoring over the integers, 1 and 3 are my only options. And I can see they're going to have opposite signs in order to give me that negative 3. So one of them's positive, one of them's negative. And then when I combine them, I need to get to negative 2x. Whatever number I put here, I'm going to have that many x's from my outside term. Whatever number I put here, I'm going to have that many x's from my inside term. They have to combine to give me negative 2 copies of x. So it looks like I want that bigger number, the 3, to be negative. So I'll try x plus 1 times x minus 3. Quick check. Outsides are negative 3x, insides are plus x. That does give me negative 2x. The first terms give me my x squared. The last terms give me my minus 3. Now, once you've got it factored, if two things multiply to give you 0, one of them is 0. So either x plus 1 is 0 or x minus 3 is 0. This would mean x is negative 1, and this would mean x is 3. So I'm going to have a point here, negative 1, 0, and I'll have a point here, 3, 0. I'll just point out there's a little bit of opportunities to sort of double check things. I know that these intercepts are mirror images of each other. So it should be that the axis of symmetry, which cuts this in half and passes through the vertex, is halfway in between. Well, halfway in between negative 1 and 3 would be positive 1, and that is where my axis of symmetry will be. That's the vertical line that passes through that vertex. All right, so I can connect the dots. And there's my beautiful parabola. Now, I chose to find the x values of the x-intercepts by factoring. That worked in this case. Like I said, there will be some times where your equation doesn't factor, but it does have real solutions. That's going to be when you've got messier intercepts that have some roots in the formula. So in general, if you've got ax squared plus bx plus c equals 0, the quadratic formula says that x is going to be the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay. Now, you should have seen this before. Some of you probably remember it just like that. Some of you may need to remind yourself of this, but we will be using this on a pretty regular basis through this chapter. So if you'd forgotten this, make sure you remind yourself of it. I would suggest you write it down every time you're going to use it. And a couple times a day, write it down and recite it. If you do that a couple times a day, in a week you'll have it memorized without too much work. Okay. I will just point out, we would get this by solving the version that we had gotten by completing the square. So if you go back to what we had done there, and you actually set that equation equal to 0 and solved it, this is what falls out of that. That's how you derive the formula. I'm also just going to point out that the whole thing is over 2a. But I could distribute that division by 2a and write it this way. Negative b over 2a, what I like to call the nice part of the quadratic formula, that's just the formula for the x value of my vertex. Notice in that case that gave us a 1. And then my two x-intercepts were the same distance away from this axis of symmetry, which was the vertical line x equals 1. This point was 2 to the right, this point was 2 to the left. In this particular problem, this is 2. So what you're getting is the x value of the vertex plus or minus a certain distance gives you the x values of your intercepts. But that's kind of nice because that way, if you know the quadratic formula, you sort of get for free the formula for the x value of the vertex. You just need to remember it's the nice part of the quadratic formula. It's the thing that you're adding or subtracting the same distance to get those x-intercepts.